Hari Om. Now let us proceed to the topic conductance and conductivity. As the name suggests, conductance is the exact opposite of resistance. We generally denote conductance as capital G. You must be remembering resistance was capital R. So G is equal to 1 by R. Whatever resistance is, conductance is its exact opposite. The SI unit of resistance was ohm. The SI unit of conductance is mho, that is mho, and the symbol is given. You can also denote mho by ohm inverse or ohm to the power minus 1. The conductance also has one more unit, that is Cmn, which is given by capital S. Do not write it as small s. Small s denotes second. So you must represent conductance by Cmn, that is capital S. And its dimensional formula will be the inverse of the dimensional formula of resistance. The dimensional formula of resistance is M1 L2 T minus 3 A minus 2. So the dimensional formula of conductance will be M minus 1 L minus 2 T3 A2. Now the way we have discussed about conductance and resistance, conductivity is the exact opposite of resistivity. You can also call conductivity as specific conductance and resistivity as specific resistance. So specific conductance is opposite of specific resistance, or conductivity is the inverse of resistivity. We denote conductivity by sigma. Sigma is equal to 1 by rho. The unit of resistivity was ohm meter. So the unit of conductivity will be ohm to the power minus 1 meter to the power minus 1, or mho meter power minus 1, or Cmn meter power minus 1. Similarly, the dimensional formula of conductivity is also the inverse of dimensional formula of resistivity. The dimensional formula of resistivity, as we had discussed in the last video, was M1 L3 T minus 3 A minus 2. So the dimensional formula of conductivity will be M minus 1 L minus 3 T3 A2. As resistivity also depends on temperature, so does conductivity. Conductivity also depends on some factors. Let us see. As we had discussed last time, rho is equal to m by n q square tau. And recently we have discussed sigma is equal to 1 by rho. So sigma will become n q square tau by m. From here, m, that is mass of free electron, and q, that is charge of free electron, are constant. So we can say that conductivity is directly proportional to n, that is number density of free electrons, and conductivity is directly proportional to relaxation time, that is tau. So if you increase the number density of free electrons, then the conductivity is going to increase, and if you increase the relaxation time, then the conductivity is going to increase. How can you increase the relaxation time? You can increase relaxation time if free electrons will move slowly. And when will free electrons move slowly? Free electrons will move slowly if the temperature is less. So if you decrease temperature, you are going to increase relaxation time, and as a result, the conductivity will increase. So if you decrease temperature, conductivity will increase for a conductor. So we can say that conductivity is inversely proportional to temperature. This you can verify also. In the last video we had seen that resistivity was directly proportional to temperature, and since conductivity is the inverse of resistivity, it is inversely proportional to temperature. Now, on the basis of conductivity, all the materials that we see which surround us can be divided into three types. Very easy things, that is conductors, insulators and semiconductors. The conductors have large value of conductivity because they have many free electrons, for example silver, copper, aluminium, etc. Whereas insulators have very low or zero, but it is nearly zero conductivity. No material has zero conductivity. Every material has some conductivity, but it might be in large numbers or in small numbers. So insulators have very low conductivity, for example wood, plastic, paper, etc. Semiconductors are intermediate in between these two. Semiconductors have intermediate value of conductivity. Some example of semiconductors are silicon, germanium, etc. In order to increase the conductivity of a semiconductor, they are doped. That is, some external impurity is added to those semiconductors so that their conductivity can be increased. You will read in detail about semiconductors in the upcoming lessons. Now let us proceed to ohmic materials and non-ohmic materials. The materials which strictly obey Ohm's law are called as ohmic materials. For example, resistors, capacitors, etc. These are the materials which are going to obey Ohm's law. Whereas the materials which do not obey Ohm's law are called as non-ohmic materials. For example, transistors, PN junction diode. You will read about these in the upcoming chapters. So there are some materials which disobey the Ohm's law, and these materials are called as non-ohmic materials. Next, there is a substance called thermistor, which is a combination of, the word thermistor is a combination of thermo means temperature and ister means resistor. So a temperature dependent resistor is called as a thermistor. That means if a temperature changes, the resistance value will change very sensitively. Such a substance is called as a thermistor. For example, some combination of oxides of metals like copper, iron, etc. can be a thermistor. These thermistors are generally used in stabilizers. For example, if suddenly some large amount of current comes, then the resistance will increase and the flow of current will decrease. So they will stabilize the flow of current in a given equipment. Next, as we have seen that if we decrease the temperature of conductors, then their conductivity is increasing. So some metals, alloys or pore conductors, if you go on decreasing the temperature, their conductivity will go on increasing, and after some point they will have very less resistance. That is, the resistance will become nearly zero. Let us put it in another way. You know that for conductors or for pore conductors, resistance is directly proportional to temperature. So if you go on decreasing the temperature, the resistance goes on decreasing, and after a certain point the resistance value becomes very less, so less that the conductivity increases exponentially. This property is called as superconductivity, and the material at that point becomes a superconductor. Now, as you can see in this graph, at temperature T0, the value of resistance falls sharply, and below the temperature T0, the material has nearly zero resistance, or the material has very high conductance or conductivity. So below T0, the material is a superconductor, and T0 is the temperature which is called as critical temperature. It is the temperature below which a material becomes a superconductor. Now let us proceed to current density. This might be a new term for you. So it is the amount of current passing per unit area perpendicular to the flow of charges. So it is the amount of current passing per unit area, and the area should be perpendicular to the flow of charges. Current density is denoted by J, that is I by A. And from this formula you can easily guess the SI unit of J, which will be ampere per meter square. Here you must remember that current density is a vector quantity. You might be surprised because current is a scalar quantity. How can current density become vector? Because current density, the direction of current density depends on the direction of current. Depending on the direction of current, the current density's direction can be decided. So it is a vector quantity. But current is a scalar quantity. This is because it is bound for the current to flow from positive terminal to negative terminal. But the direction of current density is not bound. It follows the direction of electric current. That is why it is a vector quantity. Now suppose an amount of current dI, very small amount of current dI is flowing through a surface area dA. Then the amount of current that is flowing can be calculated by dI is equal to J vector dot dA vector. Why we are doing dot product? Because in the definition we have that current density is the amount of current which is passing perpendicular. So in order to get the perpendicular component, we must calculate the dot product. So dI will be J vector dot dA vector. So if you integrate this equation, you are going to get the total current flowing through the surface. So the total current will be I is equal to integration over the total surface J vector dot dA vector. J is our current density. And as we have discussed already, the SI unit of current density is ampere per meter square. You can also easily find its dimensional formula, that is dimensional formula of current by dimensional formula of area. So the dimensional formula of current density will become A power 1 L power minus 2. Alright, now let us see a relation between current density and drift velocity. This is a very important relation. We have already established the relation between current and drift velocity, that is I is equal to NQAVD. Now we want the relation between current density and drift velocity. So as you know that current density, that is J, is equal to I by A. So substitute the value of I in this equation. So J will become NQAVD whole divided by A. So A and A will cancel out, and the relation between current density and drift velocity will be J is equal to NQVD. Alright, so with this, let us stop here today. We will proceed to the next part in the next video. Thank you.